Welcome to the Predictive Analytics Regression and Classification. In this lecture, we are going to continue on how to model a categorical variable as predictor in linear model setup. In this experiment, we are continuing from the previous video that we are assessing the relative effect of three toxin groups, toxin 1, toxin 2 and toxin 3 with a control group on the liver of a certain species of trout. The area of and we are measuring the how the liver is condition is deteriorating with the effect of toxin. So now we are going to consider a model with intercept as baseline. So there will be a baseline effect mu, and then there will be some toxin level theta I plus some variation, noise variation epsilon ij. That is what we are considering as yij. So our response vector y in this case are still the same. The change we see is a design matrix. Let us see the change design matrix. In the change design matrix, for the intercept, for each observation we'll have an intercept as 1, and then toxin 1 as 1, 1, 1 and 0, rest of them are 0. Toxin 2 is 0, 0, 0 and then 1, 1, 1 and then 0, 0. So for each level we will, so whatever observation belongs to that group, we will have 1 in that label and rest of the things are 0. This is called typically one-hot-encoding or dummy variable. In the previous video, we found that if you create the label for each of the control design, each of the dummy variable for each of the labels of your predictor variable, in this case treatment, then it is going to give you a trouble in a sense. Your design matrix is going to be have a less than full rank. As a result, your design matrix will not be invertible and you will not have a solution, unique solution. So in this case, if you see carefully that actually the first column is essentially sum of the 4 columns. If you just column toxin 1, toxin 2, toxin 3 and control, if you add all these columns, you will get the intercept column. And that is mainly the problem. That means your first column is fully dependent on the second, third, fourth and fifth. So if you add directly some second column plus third column plus fourth column and plus fifth column, what you will get the first column back. This is not good thing, because in this case you will get a x transpose x, which is again the same problem. The first column of x transpose x is simply sum of the first, second, third, fourth and fifth column, and it is not invertible, so you will not have a unique solution. So solution to this is you sacrifice one of the level. So in this case we are sacrificing control as a last column control from the design matrix. Now this is our modified design matrix. In this case we have 4 columns, and now you can see the first column is not anymore sum of the second, third and fourth column, because in the last 4 rows, if you add them up, you are not getting back the values of the intercept first column. So that's how we are breaking the dependency between the columns. So we are just sacrificing one level. Whatever level you can sacrifice toxin 1, you can sacrifice toxin 2. For this case, we are sacrificing the last level, the control group. This gives us the x transpose x matrix 16, 4, 4, 4, 4, 4, 0, 0, 4, 0, 4, 0 and 4, 0, 0, 4. And we have a nice x transpose x inverse in this case. And now my request is to try yourself, solve this and find the beta hat by hand. So pause the video, try to solve the beta hat and see if the solution matches with the my solution. I hope now you are back and we can now look into the solution, check if your solution matches with my solution. So this is my solution: 13, 10, 20 and 17, 7.25. 13 is mu hat, 10 is beta 1 hat, 20 is beta 2 hat and 7.25 is beta 3 hat. I hope your solution matches with my solution. So for toxin 1, if theta 1 hat is mu hat plus beta 1 hat, which is 23. For toxin 2, theta 2 hat equal to mu hat plus beta 2 hat is 33. For toxin 3, theta 3 hat, the mu hat plus beta 3 hat is 20.5. So you can see carefully this 23, 33 and 20.5 is actually the sample mean or group mean of that particular toxin group. You can go and check it out. And for theta 4 hat is mu hat is 13, which is the sample mean of the group of the control group. So mu hat is essentially representing the control group. If you sacrifice so that's why you don't need the baseline. So mu hat is creating as a baseline, and then beta 1 hat is the difference between the baseline and the toxin 1 group. Beta 2 hat is the difference between the baseline and the toxin 2 group, and beta 3 hat is the difference between the baseline and the toxin 3 group.